So we already looked at the three-membered transition slash intermediates. We're looking at our electrophilic addition. So now what we'll do is shift to our 4 plus member. So plus because we can see 4, 5, and 6 membered rings form through these individual reactions. So if you remember as a review, we've got the general mechanism written down there for you just to give you an idea of what's going on. We have our alkene, or really we should take a step back from that and we'll see why that's important in a second. We see the non-polar pi bond, and that's going to be important. Our non-polar pi bond act as a nucleophile and share electrons with some kind of Lewis acid, okay, or electrophile. Either's fine, it doesn't really matter which one you want to call it. The big difference in this mechanism is that the resulting leaving group, because we've now exceeded our octet on that electrophile, that resulting leaving group is so incredibly unstable that it can't exist on its own. In the previous scenario, we saw that leaving group kind of chilling out on its own. In this case, it cannot do that. So because of that, it immediately reacts back with the alkene. So if we were looking at general forms of kind of reactivity, we're looking at a negative coming from one carbon to the positive of our Lewis acid, the negative of our leaving group now going to the positive or the forming positive of our alkene. That reaction all happens in a single step. So I can't stress that enough. It's a single step that those two arrows are happening, which means that the Lewis acid and our leaving group are added to the same side of that pi bond. This would be a syn addition. Similar to the three-member-ish reaction, we might have a follow-up reaction. It's a little bit less clear in this scenario because we don't have anything charged or obviously charged here. Whereas in the first scenario, our three-membered rings, we did have that Lewis acid shown initially as charged. So we may or may not get a second step. It depends on what's on there and what our reactivity is. So again, the structure and the mechanism are what's going to force our stereochemistry and regiochemistry, so we really have to keep an eye out for those. So, admittedly the slides aren't the best designed here, but I'm trying to run a crossbreed between the focus that I see happening within this and how our textbook is splitting it. So our textbook in chapter 12 only addresses the boron reagent, and they don't really fit it in this cyclic system. So what we're going to look at here is kind of some add-in examples. So sure, borane does fit the bill. So that if we were to go through and look at this, we've got our alkene, the electrons dump to the boron. Okay? That's going to become important as why that would happen in a second. This is then going to eject a hydrogen as a leaving group, but not hydrogen, hydride, negative hydrogen. That is so incredibly stable that immediately reacts back down. Okay, so that's a bad leaving group. What we'll see happen in chapter 25 in the two sections that you're expected to look at is we'll look at a couple other reagents. We'll look at ozone. And ozone is an interesting one, negatively charged. And then this would be positively charged. And you might go through and reference that this carbon is our electrophilic site, and it turns out it's not. Okay? And what happens instead is that our alkene dumps electrons to this oxygen, which shuttles electrons to that oxygen, stabilizing that positive charge, and then we see those electrons come out. And we would form a 5-membered transition, or a 5-membered ring. Okay? In the first case, we had a 4-membered ring. We'll see yet more examples with our metals, and we'll typically see this with our oxygen metals. We'll see it with permanganate, which is what I'm drawing. And why am I blanking on the other one? Oh, osmium tetroxide. But the same kind of scenario happens. That metal center helps to kind of coordinate and shift the electrons around the ring. These are negatively charged oxygens. Our electrons come out, react. The leaving group now is a pair of electrons, in very loose terms, pair of electrons. Okay? due to the proximity of that negative charge, we again go through and form that 5-membered ring. So we're trying to look at how those electrons shift around. And again, we're looking for patterns. If we can find patterns, that can help us memorize or group these reagents so we can better understand what's going on with them. Okay? So for the sake of chapter 12, and arguably for your sake in the final exam, because the boron reagent is more important, is what's going on with it. So if we look at boron, it would be neutral. We'd say, well, why would that accept electrons? Well, to answer that question, we'd go to hybridization. And the hybridization of that boron is sp2. That sp2 hybridization means that there is a leftover empty p orbital. It is that empty p orbital that our alkene is dumping the electrons into. This now kind of exceeds the balance of electrons that our boron wants, which is why it ejects hydride. But hydride, being incredibly unstable, remember our patterns, immediately comes on and reacts backwards, or reacts back with the alkene. So that becomes important because that's explaining the chemistry with how this reaction works. Okay? And we can align it a little bit better if we look at p orbitals and all that fun jazz. We can take our borane structure, hydrogen, boron, and we'll turn it on its side now. And there's a p orbital. We're taking our electrons, putting them in, closing that out, putting those in. Okay, so it's the orbitals that are showing that overlap, which is allowing the chemistry to occur. We'll see boron show up in a variety of other locations. And in fact, we already saw it show up with an issue with borohydride when we were looking at the mercury reaction. Okay? So it was a good source of hydride. Why? Because it wants to eject that hydride. Right? It doesn't want to be negatively charged. Sodium borohydride temporarily stabilizes it, allowing that reagent to actually exist for a significant period of time. The big thing that comes out of this, which is conveniently not shown here, is that if we look at the stereochemistry of our product, because this is all happening at the same time, those groups stay in that alignment. Okay? So we would get the H and the BH2 added to the same side of the pi bond. Okay? That's going to become really important because that's addressing our stereochemistry, okay? Those original alignments. Complication that we got to worry about is that we now have a sigma bond that can freely rotate, and so sometimes you won't see it drawn exactly the way it's supposed to because they're drawing it in the lowest energy state, which might mean a rotation, okay? Because in this case, we're in a high energy state with that steric repulsion. And in this case, we're looking at them on the same side, so Z on Z same side. What I bet I was trying to ask here was, what if this was 2E, where they were trans? Okay, so instead of one being wedged, it was dashed. Okay, well, we're going to still get the same attack. That attack doesn't change, but the stereochemical alignment of those pieces will change, okay? And that becomes important. For those of you that are really good at citing your stereochemistry, you might note that we don't have a stereocenter over here, which kind of removes some of this argument. Okay? I would argue it doesn't remove the argument. Okay? We're just simplifying it and making the picture look easier to interpret. We're still getting the same stereochemistry issue pop up. That is not officially a stereocenter because there is an implied hydrogen. The other one does have a stereocenter because we're looking at hydrogen, CH3, and the boron. Those would be three distinct things, so that would be a chiral atom. Back to our addition reactions. Did the borane have to react from the top pi bond? Nope. Could have attacked from the bottom, which means we again get the potential for two different products. So you should always say, yes, two different attacks can happen, resulting in two structures. The relationship between those structures is going to dictate whether you have multiple products or not. Okay, so you have to dig into those a little bit more. The need to continue. Okay, so we did already address this in an older slide. We don't want boron on the structure, so it does end up getting ejected. And it's going to get ejected by a follow-up reaction, which we'll show the mechanism at the very end of this. peroxide. There are a variety of ways that you can go through and deal with that, but ultimately I think the easiest way, whoops, that was not the button I wanted. The easiest thing to kind of go through and do is that recognize that this set of reagents will add H and OH. This set of reagents will add H and OH. This reagent, okay, with that sometimes will add OH and OH. So if you start to memorize what those end results are, that will help. You still need to know the stereochemical output that comes with it. So you can memorize what the product is and all that stereochemistry that gets tied to it. Or if you have an understanding of what's going on with the chemistry, the reactivity, all of those things are kind of necessary byproducts of that process. Knowing the chemistry requires more time and practice. Memorizing requires that you keep it straight in your head, and that's the challenge. Okay? So you will note these two result in the exact same addition, both H and OH. Why would we have one versus the other? Okay, well, that's really going to come into play when we go through and look at the mechanism, which we technically already did. So what's the deal? Okay, what's going on with that? Why would I need two different reagents? So we'll go through and look at it, but we'll look at it in the context of actual examples, which we'll see here in a second. Okay? So again, just to reiterate, the secondary reactions are usually used to cleave the odd elements: boron, mercury, osmium, okay, manganese, ozone. Most of those cases, we don't really need the mechanistic detail behind them, and so we're going to skip that. I do apologize, that is a bit rough, but sometimes we just got to simplify life. Okay? So that's where having those things memorized can be better for you. So removing boron in the second reaction, we've got our structure drawn up here. What would happen? We'd follow that up with peroxide. Peroxide's going to end up ejecting the BH2 and replacing it with OH. Note a very interesting observation. See where the OH is located relative to the H? It's added to the same side, the exact same position as the boron. Okay, so this step could be referred to as a stereochemical retention. We're not inverting it, and we're not getting a mixture. It gets a retention of stereochemistry, and that's kind of neat. That falls out of the mechanism, which again, questionably don't need. Okay, which sets us up with some practice. So again, hit that pause button, figure these out. And we'll go ahead and start it off. I remember how I said I'd talk about mercury. Okay, so let's go through with that very first example and kind of address a couple ways to go through and do it. Well, we could go through and say, well, we add H and OH. Smart work is going to flip out here because you've now specified a hydrogen in a position. Once you specify one, you have to specify the other. Okay, where was that other one? It started with our structure. Okay, if we were to have run this with the mercury reagent, and I know mercury begins with M, but the symbol is HgOAc squared 1, step 2, RBH4 minus. This is going to result in the exact same answer. Okay? And we might go, well, so why do I have two reagents? Well, one option could be toxicity, right? But the other option actually has to do with the chemistry. But this starting material does not allow us to see that chemistry. So what we should do is move to a different reaction and see what's going on with that. If we go ahead and slide, let's go ahead and just go down and see what happens with this one. Well, it just adds H and OH, right? So we just get H and OH. Well, this one's a little bit different from that previous reaction, because in the previous system, was there a difference between the two positions that I could have placed the H and the OH? Well, no, they were chemically identical. If we go through and look at this one, note the chemistry is different. Okay? How do we know that chemistry is different? That's because we've spent that time and listened to our instructor who said that we need to be super familiar with resonance to acknowledge that that is our primary resonance contributor, which is where our balance of charges is. How is that going to affect the end result? Well, we might still go back and say, well, H is positive. Well, positive to positive doesn't make any sense. And OH is net, and no, that doesn't make any sense. So clearly, Mike must be wrong here. Right? This is why we look at the chemistry. Right? Our BH3 reagent is our boron and our hydrogen. And in this case, the boron is the electrophile. It is the positive species, which means our electrons go here, and our hydride goes there, which means our kind of first step product would be our hydrogen here and our BH2 here. Okay? The second step is that our peroxide comes through, and if we had memorized that system, we would know it places it in the exact same stereochemistry. Oh crap, I didn't specify stereochemistry. Right? Well, if we go back, wedge and wedge, this would be dashed, right? Or they're both dashed. So we would get two products from that. They would be enantiomers, which means when we get down to the bottom, they would be enantiomers. So we would also get an enantiomer. Right? Because we specified the stereochemistry, the boron retains that chemistry and it stays wedge-wedge. How does that boron chemistry work? Well, just like it had that empty orbital, if we go through and look at the peroxide, this is technically the wrong mechanism, but it works really well to explain it. Our electrons can go in, causing these electrons to go out and those to go there. The net result is that everything smooshes in the exact same location. We don't get any inversions. We're getting the exact same orientation of everything. Okay? That is technically the wrong mechanism, but it's close enough to it that it works to explain that orientation. All of that said, we still didn't address the mercury reagent. And if we went through and looked at the mercury reagent, HgOAc, let's just say it was positive to begin with. Since it's positive, our electrons come out, go in. We would form that goofy three-membered intermediate. Okay? Stereochemistry, so let's go ahead and show them as wedges. Mercury doesn't want to, I guess I need that OAc there. Mercury doesn't want that positive charge. Water comes in. Because mercury is a good leaving group, our water attacks the most substituted position. After a couple steps, we end with OH. Interesting. Note the OH is at a different position. This is where we encounter the term Markovnikov and anti-Markovnikov, or a better statement, as our tutoring center would suggest, would be non-Markovnikov. Nikov, and then this one is Markovnikov. I think it is stupid to reference Markovnikov. Not because he didn't do, butchered that spelling, not because he didn't discover something interesting and useful, but that chemistry was really addressed prior to the understanding of electrons. We're naming a reaction about an observation, a qualitative observation of where hydrogen ends up in a reaction. That's it. We now know something about electrons and orbitals and where things are. We can use those orbitals to dictate the results, not some archaic, long dead dude that is meaningless to the chemistry. Just my 2 cents. So if you want to memorize Markovnikov, non-Markovnikov, you will hear and watch me flinch like crazy, but I will accept it. Okay? What you should be looking for is the chemistry The chemistry is harder. It takes a little bit more practice to deal with, but you can do it. Okay? And that chemistry will help ensure that you get it right further on down the road. If we move to the next one in the upper right-hand corner, hopefully this one becomes even easier still, because we could go through and we can go, oh, well, it's an asymmetric system again. It goes cringe, anti-Markovnikov, and I want my OH out there. Okay? Don't like it, but hey, if it gets you the answer, great. In this particular case, we can get that answer quicker than we could down with the lower left, because the lower left had stereochemistry that we had to be a little bit careful with. The upper right, there's no stereochemistry to worry about, so we're kind of in the clear, and we can Markovnikov it out. Right? Bottom right, this one becomes a little bit tricky, and this one tends to trip people up because they go, oh, I don't know how to do this because it's an alkene. Remember how earlier I said we need to be careful? We don't reference it as an alkene, it's a nonpolar pi bond. This is still nonpolar pi bonds. It just happens to be two of them. Right? So I don't care. Do the nonpolar pi bond reaction. So we react it once and we would get the OH. Okay? We could arguably react it a second time, whoops, and lose the other pi bond, and we would end up with two OHs. Okay? Again, we're putting it at the Markovnikov position. I would argue that this step that we just undertook to do it a second time was bad and we shouldn't have done it. Okay? And we should have stopped right there at the red structure, and we should have remembered from that video talked about back in chapter 7 that what we've got here is not a nonpolar pi bond. What we have here is an alkene and an alcohol. Those two functional groups have gotten so close to each other that they have become a new functional group, and we end with an enol. The enol tautomerizes very quickly to the carbonyl structure. This is the keto-enol tautomerization, and we end with an aldehyde. Okay? That chemistry becomes a little bit trickier to deal with. We're running short on time. You got to make sacrifices somewhere. Make your decision wisely. Okay? There's the big mechanism if you really want to address it all the way through. It is more correct. It is still going to do the exact same thing that I addressed, because we're still going to get retention of stereochemistry when we go through and do this. It's a little bit less apparent when we look at it in this gory, detailed mechanism. It's lovely. I appreciate it. Sometimes you need something to help you actually understand what's going on. The shortcut that I gave you works. With that, we're done. Thanks for listening. I appreciate it. And we'll end.